The electrical signal that's going to comprise your radio transmission is generated in your transceiver, and you can measure it with a voltmeter or with an ammeter. The radiated signal in its electrical form coming from the transceiver is voltage and current. And as we just said, the antenna is the transducer where the voltage and current turns into a radiated radio wave. And the way you connect, the way you get the voltage and current out to the antenna is with something called a transmission line or a feed line. So we're going to talk about feed lines now in this. Nuts. Now, the most common feed line, and actually over the technology of radio, there have been some very clever ways to get the energy out to the antenna. But that's stuff you talk about when you're just chatting. For the test, we're going to talk just about coaxial cable. The coaxial cable, imagine there are two cylinders, a small cylinder and a large cylinder, and they share the same axis. So they are coaxial. That's coaxial cable. And in this cable, there's current in the center conductor, and it returns in what's called the braid, the outer conductor. And it sets up a field inside the cable. And it's filled with something called a dielectric. That can be a plastic foam or it can be air. But there's all kinds of coax. Some of them have braided center conductors. Some of them had solid center conductors, but the braid is usually woven like this. This is what they look like out in the field. You can see it's got. I forgot to mention that the cable is protected by an outer jacket because you don't want to change you want a stable environment between these two conductors. And that means if you get water in the cable, that really messes things up. It changes the way the signal goes down the cable. Also, it creates corrosion. So you want to keep water out of your coax at all costs. And to do that, they put a rubber jacket around it, the black rubber vinyl jacket. So here you can see the vinyl jacket and the coaxial cable. There would be a connector here on this antenna that would feed through this coil of wire to the driven element. And here also is another means of feeding an antenna, but a coaxial connector goes here. The cable comes in from your shack and gets put onto the antenna. Now, the most commonly used coaxial cable is 50 ohm cable in typical amateur radio. That's the impedance of the cable. There are other impedances and they have their use, but 50 ohm cable, that's the most common one, and that is a question on the test. Now, remember I said there's dielectric in here. As the frequency goes up, look what happens to the loss. This is a graph of loss in decibels per meter versus frequency. And for different kinds of cable. Cables have designations. They start with RG, and there's RG58 or RGX or RGU, RG213, all kinds. But for coaxial cable, actually for all kinds of cable, loss increases as frequency goes up. And the reason for that is it's the dielectric loss. The little molecules in the dielectric are affected by the radio wave, and the higher the frequency, the more they vibrate and the greater loss. The more the radio waves turn into heat. That's not on the test, but I always like to give people a physical handle to remember it. But as frequency goes up, there's more loss. Now, the kind of connectors, there's several kinds of connectors that you can have on a cable. Here you see something called a PL259. That's the most common connector at HF frequencies between 3 and 30 megahertz. It's also called a UHF connector, but is a PL59, PL259, and that's a military designation actually. But this is a PL259. So absolutely the most common connections you're going to run into are coaxial cable with a PL259 on the end. Now, this particular connector was developed in the earlier days of radio, and as they went to higher frequencies, they found that it didn't give a good transfer of energy and it leaked. So they came up with a better connector called an N connector. This is a type N connector, and type N connectors are more suitable above 400 megahertz. And for the gender of the connector, this is a male UHF connector. This is a male type N, and this is a female type N. You look at the center conductor to tell. But this is a type N connector, and it's used above 400 megahertz. So for the test, just remember, PL259 is at HF and some VHF, but type N is at 400 megahertz. Now, you don't have to have dielectric. You can have air. And the earliest coaxial cable had insulators and we just had air on the inside, and very high power stuff had nitrogen in it. But there's a problem with water getting in. You want to prevent water absorption. So if you don't have dielectric, you don't have as much loss. The only loss you have is the copper loss. The two sources of losses in the cable are copper in the braid, excuse me, I got the hiccups, in the center conductor and in the braid, and dielectric loss. Well, guess what? If you take the dielectric out, you have less loss. So coax with a hollow center conductor and no dielectric has low loss. That's air core coaxial cable. And this dielectric can be foam or it can be solid, but the air core is lower loss, but it's trickier to use because it lets water in. Again, the most common cause for failure of coaxial cables is when you get moisture inside. So that's the kiss of death, because it changes the characteristic of the medium that the signal travels through, and also it corrodes things. So here's an example. In addition, when you have loss is a reduction in signal level. You have gain, which is an increase in signal level, like antenna gain, but you also have loss, which is a decrease in signal level. And in a coaxial feed line, also called coax, you can get loss through water getting into the coaxial connectors themselves, creating corrosion. And if you have a high standing wave ratio, that's you have more loss. We'll get to that in a bit. Or if you have multiple connectors in the line, and all of these will cause loss. Turns out each connector will cost you about 1/10 to 1/4 of a dB. Here, the outer jacket, polyvinyl chloride or PVC outer jacket, is broken. Now the water, it's waterlogged because it got water in it. And you can see the copper braid is turned green. Now, the outer jacket of the cable should be resistant to ultraviolet light, because that can damage the jacket and allow water to enter the cable. Now, there's a difference also between smaller and larger cables. Here's an example of a small cable, which is RG58, and a large cable is RG213. And the loss in a cable, besides depending on the dielectric, it's a question of geometry. And it works out, if you slog your way through all of the mathematics, larger diameter cables have lower loss. That's just the way it is. All things being equal, a larger cable will have lower loss than a smaller cable. So why don't we always use larger cables? Because sometimes they're mechanically more difficult to use than a small cable. So the electrical difference between smaller and larger coaxial cables is that the larger cable has less loss. Now here, this is a screw up. The difference between RG58 and RG213 should be is that the RG213 has less loss. And here you can see some losses for typical losses in cables per 100 feet. But these are all the same, pretty much the same, because they're all large diameter. The lowest loss at VHF and UHF is air insulated hardline coax. And I don't think that's LM400 either. Joe, do you know if LM400 is air insulated? I don't think it is. I think it's
No,
just
LM400 uses like a foam insulation on it. It's very low loss. It's very high quality cable, but it's got, it's some kind of a foam.
okay. Thank you. Yeah, they'll use foam to trap air bubbles in there.
Yeah.
But anyway, the lowest loss is in air insulated hardline. Hardline coax means that the braid is not woven. It is a solid piece of copper. So air insulated hardline has the lowest loss. And again, the rule of thumb, just remember this, bigger cables have lower loss. Bigger meaning larger diameter. Now, the way you measure your losses is with something called an antenna analyzer. And you can measure whether the antenna is resonant or not. An antenna analyzer, also called an SWR, standing wave ratio analyzer, is an important part of your test equipment if you regularly work on tuning your antennas. Turns out the SWR will be the least when the antenna is resonant. But you use this, here's a couple of examples, to tune your antenna by measuring something called the standing wave ratio. Now, how well the load is matched to a transmission line is measured with a SWR meter to show the standing wave ratio. See, whenever you go from one medium to another, you got to make sure your power transfers. So you got to make sure that your transmitter transfers power to the transmission line, and then up at the antenna, the transmission line transfers the power to the antenna. And there's always, unless it's a perfect transfer, you always get a reflection of some kind, hopefully a little bit. But if you have what's called a mismatch, that's where the antenna does not accept all of the energy and it reflects some back. So here you can see, here's your original signal heading towards the antenna. The antenna accepts most, but not all of the energy and reflects some of it back. And if you try to measure that on the line, you're not going to measure the original and the reflected signal. You're going to measure a combination called a standing wave. So when you consider an SWR meter, you need to know what frequency and power range you're going to be for your particular use. So one SWR meter does not work at all frequencies. You got to make sure it works at the frequency and power level you want to use it for. And I told you the truth, but actually some of the analyzers will discriminate between forward and reflected power. Here an analyzer has 2 meters and here it's reading about 70 watts forward and about 6 watts reflected. An inline SWR meter should be connected to monitor the standing wave ratio of the antenna system in series with the feed line between the transmitter and the antenna. So that's where you want to measure the forward and reflected power in the transmission line between the transmitter and the antenna. Now, this is another thing you got to be careful of. The question pool asks this question, but it says a power meter, okay? And this is important enough that I want to just pause for a second here The question is, where should an RF power meter be installed? And the answer is in the feed line between the transmitter and antenna. You'll notice here they say an SWR meter, but the question says power meter, not SWR meter. Now, did you ever, when you were a kid, take a clothesline and tie it to a tree and wiggle it up and down, and you get something that looks like this? That's called a standing wave. And that clothesline, you're seeing the wave being reflected from the tree or whatever, and you get this figure 8 thing. This is called a standing wave. This is a combination of the incoming wave, and in this case, the surface accepts none of it and reflects all of it back. And this is a standing wave. So here, now going to a transmission line, going out to your transmitter, you see the signal from the transceiver, and you see the signal reflected from the antenna, and you see the sum of the two waves. Now the question is, it's important to have a low SWR in an antenna system that uses coaxial cable so that you get efficient power transfer and reduce the losses. See, if you have, if you're forcing the antenna to accept power, you can do that, but the reflected wave will also cost you energy coming back from the antenna. So the signal going to the antenna dissipates a little bit of energy, and the reflected signal dissipates energy. So you want to minimize the reflected power to reduce losses on the line. And the middle point here is called a node. That's where the zero crossing is. The voltage at the node is the average voltage compared, the median voltage compared to ground. Now, if you get a reading of 1-to-1 on an SWR meter, that's a perfect match between the antenna and the feed line. That means the antenna is accepting all of the power and reflecting none of it. And that gives you, there's a way to calculate, but 1-to-1 is a perfectly matched antenna. And as you get higher readings, 1-to-1, 1.5-to-1, 2-to-1, 3-to-1, 4-to-1, the higher the SWR, the worse match you get. And high SWR, the reading of 1-to-1 indicates a perfect match on the antenna and feed line. But if you have a high SWR, that means something is wrong. And again, standing wave ratio, there's a physical reason for that. Back in the days before we had instruments like this, people would measure the voltage, the minimum and maximum of the standing wave on the feed line. And that was the standing wave ratio. If there was no reflected power, everywhere you went along the line, you measured the same voltage. But if you had big reflections, some places you'd measure 4 times the voltage than you would other places. And that means you had a lot of reflections. So that's what a standing wave ratio means. Just think of the clothesline in the tree. But the question on the test says, hey, higher standing wave ratio means something's wrong. So you want a low SWR. Here with a SWR of 4-to-1, there's an impedance mismatch. Now, some transceivers have an SWR meter built in. Here's a Kenwood 440 that has one built in, but here's also a power meter, an RF watt meter that is directional that'll measure forward and reflected power. Now, you can have meters that will have dual meters that will measure forward power on this scale and reflected power on this scale. They'll measure it at the same time, and where they cross will give you the SWR, the standing wave ratio. So, excuse me, to protect the solid state output amplifiers, vacuum tube outputs were pretty robust and you could abuse them, but solid state transistors at the output of your transceiver won't take much abuse with reflected power. So solid state transmitters have a safety feature. If the SWR increases beyond a certain level, they reduce the power output automatically. That's called fold back. But again, to protect the solid state output, there are transmitters that will reduce the power if they see they're looking into a high SWR, if they see a high reflected power. Now, if you're getting erratic changes in SWR, that means you got a loose connection somewhere. Something is mechanically inconsistent in your system, in an antenna or in a feed line. Now, a directional watt meter is an instrument besides an SWR meter that you could use when the antenna is properly meshed. Here for the bird, if you turn the slug to the right, it measures forward power, like power coming in the left and going out the right. The arrow on the slug will measure power in that direction. And if you turn the slug the other direction, it'll measure the reflected power. So what it does is it measures forward power and reflected power in watts. And then you have a lookup table that tells you what the SWR is. So here, turn the slug to the right to measure the RF output, turn the slug to the left, and this is wrong here. You measure the reflected power and then you look up the SWR. So generically, yeah, you're measuring SWR, but to the left, you're measuring actually reflected power. But a directional watt meter is the one, let's see, that's C7, C8. That says what instrument can be used to determine SWR. And the directional watt meter is the way that that's done. Now, instead of turning a slug, there's other watt meters that you just flip a switch and it'll give you forward and reflected power. Now, so if you got an SWR problem, how do you reduce reflected power? Well, you have what's a device, it's an impedance matcher. Like it'll hook up to your transmitter and hook up to the transmission line, and your transmitter really wants to see 50 ohms impedance. And so this is an impedance matching network that will take whatever's it's looking at to the antenna and transform it to a 50 ohm impedance so that your transmitter is happy. It will tune out the reflected power. So an antenna tuner matches the antenna system impedance to their transceiver's output impedance. Now, when you're testing your antenna and stuff and your transmission line, you don't want to radiate power because that's bad practice. You interfere with people. So you have something called a dummy load that prevents radiation of the signal while you're testing. This is just a big bad resistor that can dissipate a lot of heat. Here you can see it has air, ventilation. This is a paint can that's full of mineral oil, actually. Used to be transformer oil, but they usually use mineral oil now. But this is a big transmitter or a big resistor, and as you dump power into it, the resistor is going to get hot. Just like here, you dump power into it, the resistor is going to get hot. Here, it's air cooling to remove the heat. Here, there's oil circulating in here. You're basically warming up the oil with your load resistor. Sorry. Okay, that's all. Are there any questions here? Okay, I will stop sharing and pass it over